Okay, so what we want to talk about today is how queries are executed in the database. Now, it's exactly what you are doing right now, right? You basically are actually simulating how queries are implemented in database for scanning a table and for scanning an index, right? So this is exactly what's happening. So the whole point of this homework to give you a mental model of what it's like. So whenever we talk about query execution, one of the things we care most about is how many data pages are read in and out of disk into memory, right? So basically, really what we do care is number of data pages that I had to read to answer this query. So one of the things that we will get used to, as I mentioned, is whenever I talk about the cost of a query, it is the total number of pages that are read and written. The reason we look at the number of pages is that once you bring the page into memory, the cost of doing that is so much higher than anything that you do in CPU, is that that's the dominant cost. It doesn't mean that the CPU cost is negligible, but it really is the dominant cost. So we are going to really care most about the number of pages read and written. So why pages are written, that will become obvious when we go a little further. Right now, what we care most about the number of pages that I read. And that's exactly what you're doing in this homework, so that kind of gives you an idea of what you do. So, now the other thing that you realize is that the data that you have often is much, much larger than that would fit in memory. So data is too large. I cannot read everything all at once into memory and then do everything that I want. So there are two reasons for that, right? So data is too large to fit in memory. Well, for one, it could be that your data is, in fact, terabytes of data, right? You don't have terabytes of memory on your machine. So in fact, you might have legitimately too large data. Or it could be that you have smaller data, but you have lots of concurrent users, right? So each one has to execute queries in parallel. So that means that they cannot really all at the same time have all the memory in the machine, right? So you actually have to partition the memory that your computer has between different users. So that means that, and partition to multiple users. So technically, you can imagine that each query has some limited amount of memory that it can use. So we are going to talk about these two things. So these are the two important things, right? You cannot read all the data into memory and do everything in memory, because it's going to be massive. And this is just one table. So what if you actually join two tables and the output is huge, right? So it doesn't fit in memory. So we are going to say that often whenever we write any operation, we assume there is some bound, let's say, and memory blocks available to a query. And each memory block is the same size as a data page. And I'm going to assume that my relation has pages of R pages. Okay? So these are the two important things to remember. Each operation has a limited amount of buffer or memory. We call also this buffer. And it is possible that this M is much smaller than the total number of pages for R. So for example, when you are executing a sequential scan, right? So do you read all the pages all at once into memory? Or do you read one page, process what you want, and then read the next page? don't work, how would you do sequential scan? Do you read one page at a time, or do you read all the pages, read everything into a list? One page at a time, okay? Because you don't need to really, have everything in memory to find if a tuple is in the output or not. Yes, I just index. I just index from 1 to however number. Yes, you can. Hard coding is okay. I don't want you. I want all of you to kind of get a sense, but not kill yourself. So, okay. So basically, that means that in fact, this page scan I can do with one block at a time, right? So generally, imagine that each operation works as follows. So you have some number of pages and pages that are available to your query. Relation R is stored on disk. And then you read this into M. Sometimes you may need to write it to some temporary storage. And when you are done with your query, you know that certain tuple has to be in the output. You output it into the buffer, so you send it to the output. Now, what is the output generally? Like when you write SQL, what is the output for you? Tuples, but where does it come? Where does it go to? Standard out, right? Just print on your terminal, right? So basically your output is just put into your standard output. So that means that once the output is there, I just send it out to the world. I don't need to store it somewhere, right? But to actually compute things, I have only these M pages, and I may need over time to write things back to this and so on. Well, once I'm done, it is written down. But one of the things that happens is that when you actually write a query, so something like select r.a, s.b from r and s, where r.c is equal to s.c, okay, and distinct. A query like this basically gets translated into, and let's say another query, and r.d is equal to 5. A query like this actually gets translated into a query tree. And you're going to see that after we are done with this part. But you're going to have given r, select r.d is equal to 5, then do a join with s on r.c is equal to s.c, then project on r.a and s.b, and then remove duplicates. Okay? So basically, what happens is that your SQL gets translated into a query tree. And then you find different ways to implement each of these operators. And there are, in fact, multiple ways to implement each of these operators. That's what we're going to talk about today. But the thing that I want to mention here is that this notion of read the relation and output it to output buffer doesn't really work for the intermediate operators, right? So whenever this is finished, this can put the output to standard output, like this. But for the others, they basically have this relationship that tuples that are produced by lower relations actually are fed into the upper relations. So basically for these, the input buffer for this is actually the output buffer for this. What that means is that whenever I have the join and I find tuples in the join, I put it into the output buffer. That output buffer happens to be the input buffer for the projection. that it will take and do things with. So to be able to chain operations like this, database operators have basically this interface that they all implement. And this is called the iterator interface. Those of you who are interested in software engineering, this is actually pretty cool. So each operator has the same exact interface, so I can chain them together. So basically, they support three basic operations. One operator is open. Basically, this is like initialize. So what you want to initialize is the input-output buffer, right? So you basically figure out that I'm going to read this relation is stored on this page. You read actually, page 1. So, you look it up. And then you realize I have 10 disk pages for this query, so you allocate those disk pages. All of that is part of open. So allocate memory and initialize structures. All right. All right. I'm saving you of that. So, and then the opposite of this is close, which will, whenever your operation is finished, it will do the reverse. It will deallocate memory and get rid of all structures. So if you were to execute this complex query tree, you have to run open on all of these operators, and you have to chain the input buffer of one to the output buffer of the other. Then every single operator has this notion of get next. So the get next is basically going to execute it enough so that you can get enough tuples to fill out a disk block. So basically, get next will execute the operation to produce tuples. Okay? So what does get next mean? That it will need to basically read inputs and perform processing and output found tuples. So every operator supports this. So basically, when we are going to talk about it, start thinking about, for example, how this would work for every single query that we are going to look at. So let's try to think about the simplest possible one, which is the sequential scan that you are currently doing. So if you're doing sequential scan, or table scan, the nice thing about this is that it's actually very easy to do, because you only need one data block. Okay. So what the get next would do is allocate this block and then figure out what's the first page for R is. So we are doing, scan. So this is to answer some condition on R, right? Read one data page of R into one block, right? One page, page1.txt, read it into here. Then scan the tuples in here to see which ones satisfy C, and the ones that satisfy C, output. Now think about how getNext would work. So for this to work with getNext, here's what's going to happen. So if I need to find the next tuple in the output, I'm going to read here to see if there's any tuple that satisfies the condition C. If there is no tuples, then I'm going to go and read the next data page from R, read this into here, and then I'm going to scan those to see if there's a tuple. And then If there isn't, I will continue doing this until either I finish this or I find a tuple. So the getNext is going to actually continue reading these pages until it finds one tuple that will be in the output. Okay? So this is the general idea of getNext. And if I want to actually do getNext 10 times to read 10 tuples, it may mean that I need to read many disk pages to find the 10 tuples that satisfy the query until the query is done. So basically, the getNext itself is a simplification because it may involve reading many disk pages. Okay? So there are two things. One is that I do not need more than one disk page to execute this. In any of these computations, you never care for the output buffer, right? Output buffer is not your concern. It's the next operator or the standard out. I don't care how much buffer you have for that. But what I do care is how much memory I use for this one. So, using one block, I can answer this query. And what would be the cost of this operation? How many disk pages do I have to read to answer this query? It is the ghost of students who suffered in this room. What would be the cost of answering this query? The total cost. How many disk pages do I have to read to answer this query? See? Well, but how do you know that you have found everything that you're looking for? If C is a general condition, then it would mean that I have to read every single page. If C is a primary key, right, then it may be in the average less, right? But for now, we are going to care little about all these complications. We're going to say the cost of doing this is pages of R, which is exactly what you were asking earlier, right? So whenever you have a sequential scan, you have to read every single page, except that you are scanning on the primary key that you can stop earlier, but we are going to disregard that for now. Okay? So here is a little parenthesis here. What if m was not 1, but m was much larger? Would that speed up this query? If you actually had, instead of one block, you had many blocks, what would be the cost of the query? So instead of 1, actually m is 100. What would be the cost of this query? Come on, you can do this. This is a different world. What's the cost of this query if you have 100 pages? Yes. But you still have to read every single page of R. Right? You just read it 100 at a time versus 1 at a time, right? But you still cannot escape from the fact you have to read every single page. Right? So, it is in fact pages of R. So your query doesn't get any faster because you have more memory. In practice, though, it actually may, because that if you are reading 100 pages at a time, you may be able to read many pages with a single scan, so it may actually be faster. Right? So it allows you to prefetch multiple pages in the same disk page, so it actually may be faster. But for what we are doing now, we are going to disregard that as well. Okay? It's very important that you get this, because it's going to get much more complicated in a second. Okay? Do you have any questions about this? Always ask yourself the question, how many disk pages do I have to read to answer this query? Right? All right, so sequential scan, you always have to read every single page, so it's pages of R. You don't really gain anything by having more memory, but you may actually speed it up because of being able to do multiple sequential scans over the disk. So, given this model, we are going to look at many different types of operators, and we are going to look at operator implementations. And we are going to look at single pass, double pass, and multi-pass algorithms. Again, I can do a multi-pass, but you will not get what that references to. Good job. You see, my husband said nobody would know what that's about. All right, thank you. All right, so let's think about different algorithms. So let's look at single-pass algorithms. All right, let's look at duplicate removal. So you want to find all unique tuples in relation R. So what I'm going to do is I'm going to split my m buffer pages into one buffer page and m-1 buffer pages. So this is for my input. So read R one page at a time. As soon as you, and then here you store the unique tuples that you have found. So this is unique tuples seen so far. So every time you read a new page, you see if that tuple is seen. If so, then insert it here. Now, if you do get next, so that means if you want to get the next tuple, then you would actually, at this point, you can actually output this. So you can keep track of the tuples you have output so that you can actually get something new. And if you want to get the next one, then you have to read enough data pages to find the next unique tuple, right? So you cannot just necessarily find it all in a single page. So read one page of R, do this. When you are done with this, this page is now empty. Read the next page and continue doing this. So what is the cost of this operation? Pages of R, all right? Pages of R, except only if, after you remove duplicates, the remaining data actually fits in n-1 buckets, right? So only if all of delta R fits in n-1 blocks. Because you actually have to keep track of all the duplicates, all the unique tuples so far to know whether you have actually output this or not. So as a result, you cannot really get rid of tuples you have seen because then you may actually output the same tuple multiple times. So if actually the duplicates do not fit in n-1, that there are in fact huge number of tuples in the output, then this will not work. You cannot do it in a single pass, then we have to have a different algorithm. Remember, I keep telling you to not use distinct unless you need to, because it could be very costly. It doesn't necessarily, unless your database knows that it doesn't have to do anything like this. All right, so let's do a couple more. So let's do R union S, but set union. Now, set union happens to be actually one of the simplest operators. Bag union. Oh, actually, let's do set union. That's better. Set union happens to be a special case of duplicate removal, right? Why? Because here's what I'm going to do. First, I'm going to read R one page at a time, and then put all unique tuples here. So unique R tuples. So any unique R tuples I find, I'm going to put in here. Then I'm going to do the same thing with S. So now I'm going to take S, and then I'm going to read S again. Again, every unique tuple I find, I'm going to put in here. And if R union S fits in m-1 pages, blocks, it's the same thing. What is the cost of this operation? Yes, good job. Okay, you have to get used to this because it's going to get fancier. But only if this result fits here. Okay? So basically, set union is a duplicate removal, right? There is no difference. Any questions so far? Now, what if I had bag union? That's super easy. For bag union, I don't need to keep track of whether I have seen a tuple or not because every tuple should be in the output, right? So, so this is our union all S, right? So that means, in fact, I don't really need the space. All I need is one block, read R and output, and then read S and output, right? So read R one by one, put the tuples out, and read S one by one, put the tuples out. So as a result, I don't need more than one block. This is similar to sequential scan, and the cost is the same, except its requirements for memory is much smaller. Okay, so let's try a different one. Let's try set intersection. How do I do set intersection? So now I want to return only those values that are both in R and S, but I also need to remove duplicates, right? So things are a little bit more complex. So let's say I'm going to read R one block at a time. And I put all the unique tuples into m-1 blocks. Okay. Now I'm going to start reading S. So if a tuple in S is not in here, what should I do? I read the tuple of S, but it is not in the m-1 blocks, then I can remove it, right? So if S is not in, so if S is S tuple not in here, then discard. If it is in here, I'm going to mark it, okay? But what I can do is actually not only I can mark it, but I can actually output it, right? Because as soon as I found a tuple in the intersection, I output it. If I see the same tuple again, I will just not output it, but that's okay because this is set intersection. So else, then output tuple and remove from memory. So this guarantees that you only are going to output it once. Again, the cost of this is pages of R plus pages of S. But only if R after duplicate removal fits in M minus 1 blocks. So this is kind of a warm-up of thinking about how to implement operations using simple memory. And if things fit in memory, everything is easy. If they don't fit in memory, the first thing you can do to speed up your queries is to buy more memory. If that doesn't work, then you have to use a different method. But remember that there are lots of little things going on here that you may not really notice it now, but it actually is very important. One of the things is, clearly because of this, you want to start with the smaller relation, right? So if you have two relations R and S, whichever is smaller is the one you want to read first because you will need to give fewer tuples. If there is some sort of projection later in the query, you don't need to keep tuples you don't need. You can remove attributes. And as you remove attributes, then you basically are going to be able to fit more space, fit more tuples into the same space, so you can actually reduce things. So a lot of basic operations actually have all of these different subroutines that they can be combined with. So I'm going to stop here. Now, one of the things we're going to do next is get more fancy. So this is all great only if at least some of the data fits in memory. But if it doesn't fit in memory, if the data does not fit in memory, you have to do something different. So basically, you have two main options, right? So if data does not fit in memory, we are going to see two basic strategies. One is sorting. And when you sort data, it's actually going to be useful not for that specific operation, but maybe other operations down the line. Or if you don't want to do sorting, we're going to talk about hashing. And hashing is also equally useful. So let's stop here, give a 5-minute break, and then I'll start talking about sorting.